Throughout this course, we're going to be analyzing the runtime of algorithms. It's desperately important. So we're going to have one lecture on analyzing the runtime of algorithms. In general, analyzing the runtime of algorithms is a pretty intuitive thing, but we just like to firm up the concepts. To analyze the runtime, first we have to deal with what time is. And a time unit is just going to be a basic operation. And to count or to analyze the runtime of an algorithm, what we're going to do is just count the number of basic operations. Basic operations really fall into 3 or 4 different categories. We're either going to add numbers, multiply numbers, compare numbers, or set a value. There could potentially be other basic operations, but these are really all we're going to deal with. In some settings, we'll define exactly what a basic operation is. For example, a basic operation could be solving a linear program. In practice, when we look at runtimes, we're never going to be concerned with exactly what the runtime of an algorithm is. Instead, what we'd like to do is get a good upper bound. So we'd like to get a good, and I'll emphasize good, upper bound. The other thing to emphasize is that the runtime isn't just something that's a natural part of an algorithm. The runtime is going to be some function of the size of the problem. So it's going to be a function of our problem size. The size of the problem is going to be a little bit more fiddly than what a basic operation is. The size of a problem can really be anything at all. It should make itself apparent when we're analyzing the algorithm what size actually means. We'll go through an example to firm up these ideas. Here we have our Knapsack algorithm, and we're going to analyze the runtime of our Knapsack algorithm. Before we do, we have to define what the size is. And in this case, the size of our problem is going to be the number of items. So we'll say that there's going to be n items. Usually we're going to leave the size of the problem as some variable. Given the size of the problem, we can start to analyze how long each one of our operations takes. So for example, setting k equal to the empty set is going to take 1 time unit. We've set a value. Setting v equal to 0 is going to take 1 time unit. It's setting a value. This loop, this for all loop, is going to loop over every subset of n. There's 2 to the n subsets, so we're going to go through this loop 2 to the n times. Inside of the loop, to compute s, we have to add n numbers, so it's going to take n units of time. To compute v bar, we're going to add n numbers, so it's going to take n units of time. To analyze this if statement, we have to compare 2 values. That's going to take 2 units of time. And in the worst case, we're going to have to potentially set k to our new set s every time. So this is going to take 1 unit of time. Given these different time units for each of these individual operations, we can start to analyze the runtime of the algorithm in whole. On the top, before we go into our for loop, we take exactly 2 units of time. So this takes 2 units of time. If we look inside of our for loop, every time we go into the for loop, we have to take 2n plus 3 units of time, which means that going through all of these for loops is going to take 2n plus 3 units of time each time we go in through the loop, multiplied by how many times we go into the loop, which is 2 to the n times. So in total, the runtime of our algorithm is going to be 2 plus 2n plus 3 to the 2 to the n time units. We say that this takes time 2 plus 2n plus 3 to the 2n. This is a pretty messy expression, so we're going to deal with actually making this a little bit simpler. The way we're going to make this expression simpler is by using something called big O notation. You should have seen and be familiar with big O notation, but we'll just firm it up again. Big O notation is going to compare 2 different functions. So f of n and g of n are 2 functions of n. In our context, these 2 functions are functions of the problem size. The problem size in this case is n. And we say that f of n is big O of g of n whenever there exists a constant and some large n value, so that for all n greater than this large n value, our function f of n is less than or equal to this constant times g of n. So f of n is big O of g of n when at a sufficiently large value, capital N, g of n is going to dominate f of n. And here we have a little graph of what big O means. In this case, our function g of n is big O of f of n. We see that below this value n, the behavior of g and f of n are really kind of arbitrary. F of n can dominate g of n or vice versa. But after this large value of n, g of n is going to be larger than f of n. So f of n is big O of g of n. It's dominated by it. This is the formal definition, and this is how we're going to think about big O notation. There's a function that dominates another one. In practice, life is going to be a little bit different. In practice, what big O notation is going to allow us to do is drop constant terms, or drop constants in particular locations. It's going to let us identify, find the biggest terms, and when in doubt, after we've dropped constants, after we found the biggest terms, if we're unsure of ourselves and our expressions, that is, when we're in doubt, we return back to our definition. Now let's use this idea of big O notation to simplify the expression for the runtime of our knapsack algorithm. The runtime of our knapsack algorithm was 2 plus 2n plus 3 to the 2 to the n. We're going to write an expression and say that this is going to be less than or equal to 2 times 2n plus 3 to the 2n whenever n is greater than 10. I don't really know the specific value of n for which this is true, but certainly at n greater than 10, this inequality holds. And because this inequality holds, we can say that the runtime of our function, or the runtime of our algorithm, which is 2 plus 2n plus 3 to the 2 to the n, is going to be equal to big O of this new function that we've written, 2n plus 3, 2 to the n. Here we have this constant, and our constant in this case is 2. Our capital N is going to be equal to 10. So when we look at our definition, we have to identify our constant c, and our capital N here. Our constant c is 2, and our capital N is 10. But we can go even further. This new function that we wrote, 2n plus 3 to the 2 to the n, is going to be less than or equal to 2 times 2 to the n whenever n is greater than 100. And again, I don't know the specific value of n for which this is going to be true, but certainly whenever n is greater than 100, 2n plus 3 times 2 to the n is going to be less than or equal to 2 times 2 to the n. That is, this inequality is going to be true. This means that 2n plus 3 times 2 to the n is going to be big O of 2 to the n. Here we have, again, our constant is 2, and our capital N is 100. But we can see exactly what's happening here. Whenever we use this big O notation, we start to drop constants and find dominating terms. In this case, at the very end, we found a dominating term. To put these two things together, we can see that when we have this big O notation, it's sort of a transitive property. That is, in this case, we have 2 plus 2n plus 3 to the 2 to the n, and this is big O of 2 to the n. To get this result, we could just sort of unravel what we've done in this two-step process. This is the final answer for our runtime. It's big O of 2 to the n. That's the runtime of our algorithm for the knapsack problem. And it's important to identify that what this term inside of the big O is the term that's going to dominate our expression. It's the biggest one. 2 to the n is much bigger than, say, 2 times n, or the constant 2. So 2 to the n is the one that's going to remain. Of course, writing out all this big O notation stuff is pretty annoying. And in this class, we're generally not going to do it. We're only going to use big O notation as a tool. and we rely on the definition only when we're unsure of ourselves. In reality, this knapsack algorithm that we've written should be a very simple thing to express. To express the algorithm, we say that we're going to compare all the subsets of n and take the subset with the largest value that satisfies the knapsack constraint, that is, the sum of the SI's is less than C. To analyze the runtime, all we have to say is that we compare every set. Comparing every set is going to dominate the amount of time that our algorithm takes. And to compare all these sets takes order 2 to the n time. It's totally sufficient to say only this sentence when analyzing the runtime. We have our order notation, how long it's going to take, and we say roughly why it's going to happen. We have to compare every set. This is sufficient. The final thing we'd like to say about running times is a particular type of running time, polynomial time. To be polynomial time, it's a property of an algorithm, if the size of our problem is n. And again, the size is sort of a weird thing that will be defined for each different problem. If the size is n, and our algorithm runs in order n to the k time for some constant k, then our algorithm is polynomial. The important point here is that this k is a constant term. So, for example, if we have an algorithm that runs in order n squared time, then it's a polynomial time algorithm. We'll put a check next to it. But let's suppose we have an algorithm that runs in order n to the log n time. This is no longer a polynomial time algorithm because our exponent up here is not a constant. It's a function of n. Similarly, if we have an algorithm that runs in order n to the square root of n time, this is also not a polynomial time algorithm because our exponent, again, is not a constant k. Polynomial time is going to be important, but in general, analyzing the runtimes of algorithms is going to be essential. We'd like algorithms that run in very short amounts of time in terms of the size of the problem. Polynomial time is just some cutoff that's traditionally used to define an efficient algorithm. If an algorithm runs in polynomial time, we're going to call it efficient. So this is going to effectively define efficient.